started. Homework 4 has been illustrated. You had one break from homework, right? We will cover what we're going to discuss today. Graph-based control flow testing. I think you have 1 week to work on the assignment. Today we will see, we will try to finish control flow testing. Okay, so basically, graph-based testing has 2 parts. One is control flow testing, the other is data flow. The other is data flow testing. So we will try to finish control flow testing so that we can work on the homework assignments. So to refresh our memory, what is a basic block?
It's a section of code that had only one entry and exit, and all statements are always executed out of that block.
Is yeah, very close. Okay, but I guess from a technical perspective, we want to be very precise. So the basic block, either you execute all the statements, or you do not execute any statement. Okay. So you cannot execute some of the statements, but not the other statements. That is a very important part of basic block. We use basic blocks to create control flow graph, right? That is why we have to identify basic blocks first. I want to ask you, if we do not have basic blocks, how the control flow graph is going to look?
Spaghetti.
Spaghetti? Well, whether it is spaghetti depends on how the program is written. How you create the control flow graph is because it's basically, from a certain perspective, is an abstract representation of the underlying program, right? So when it is spaghetti depends on the underlying program, not the abstract representation process. That makes sense. So if your code is spaghetti, then no matter you use basic block or not, you're going to get a spaghetti control flow. Okay. If your code is not spaghetti, then you're going to get a clean. Okay, then you put that in. So imagine like each control flow graph, each basic block inside, if you can imagine, is a sequence of statements, right? If you do not use basic block, then as you can imagine, you're going to have a linear sequence of those statements. Okay. There will be no branch inside each basic block, right? So from another perspective, what I'm trying to say is that using basic blocks allows you to compress the graphic representation, because inside each basic block, you can imagine it will be one linear sequence of consecutive statements, right? And actually, like a control, so I guess from another perspective, the control flow basic blocks allow us to reduce the size of the control flow block. It's a kind of compression. Okay? You can compress a linear sequence, but you cannot compress branching structure. That makes sense. So you still preserve the branching structure, called the control flows. Okay. Another important usage of basic block is that we're going to do, for example, code coverage. Like if you execute a certain test case, you have to track the coverage, right? You see how many statements are executed by the test cases. that you have executed. So as you can see, one way to track the coverage is that each statement, if you execute, okay, a straightforward approach, like you're going to have a flag, you're going to indicate whether this statement has been executed. Okay, so you're going to do program instrumentation, you're going to add some statement, whenever you execute the statement, you're going to set that flag. Okay, so this statement is executed. Then after you finish executing all the test cases, you look at, you check each statement, whether the flag is set or not, then you know how many statements are executed, right, are covered by your test cases. And that's the basic idea of all the coverage measurement tools which you are going to use on your project. You have to, and we're going to give you some suggestions that you can find a lot of coverage measurement tools. So what happens is that if you have basic block, you only need to track whether each basic block is executed or not, instead of individual statements, right? Because of the property of basic block, if you execute one statement in the basic block, you're going to execute all the statements, right? So for each basic block, you only need to have one flag instead of having one flag for all the statements, and that's going to significantly reduce the runtime overhead. Okay. So basic blocks are used a lot in static analysis of programs because it allows you to reduce the amount of information you have to process. Last time we finished this slide, node coverage, basically from informal perspective, node coverage is basically like a statement coverage. Okay. If you cover every basic block in a program, you definitely cover all the statements in your program. That's what people typically refer to in practice. This is statement coverage. And the basic idea is that any statement that you write, when you test, you need to test at least once to see how your program behaves when that statement is executed. And that's how you know, right, when the statement is correct or not. And we also finished this slide, edge coverage. So if you recall the, if you look at the control flow graph, each edge basically represents a branch. Okay. If you cover every possible edge, then you cover every possible branch. Okay. So every conditional statement you have in your program. Again, the idea is it's kind of straightforward. If you make a decision, you want to test the two possible outcomes of any decision you make, right? What if I take the true branch? How my program behaves? What if I take the false branch? How the program behaves? So that's the basic idea behind node coverage and edge coverage. And as you can see, this is probably the minimum coverage we should achieve, right, when we test the program. I mean, can you imagine like you write a line of code, but you never test that line of code? It does not feel comfortable, right? I mean, at least you should test every statement. The same applies to every branch. If you have a if you make a decision, when you test your program, you should at least test what happens when the decision is true, what happens when the decision is false, right? I hope that makes sense to you. That's the basic idea behind these two coverage criteria. Right? However, what happens is that in practice, actually not many projects can actually achieve node coverage and edge coverage. And the point I'm trying to make is that in practice, people are not doing adequate testing. Okay, if you look at like what we discussed here, look at what is behind these two coverage criteria. This really makes sense, right? But in practice, many people do ad hoc testing. Okay, they do not follow the systematic strategy to generate test cases. And what ends up is that you do not even achieve code coverage, statement coverage, not to mention edge coverage or branch coverage. Another possible coverage we could achieve is called edge pair coverage. So basically, the idea is that for each pair of edges, okay, if they could be executed one after the other, then you have to have a test case to exercise the two edges in the given order. Okay? That's an intuitive way to say that, but the formal definition is this. So on the slide, TR, what does TR represent? Can you make a guess? Test requirement. Okay. Remember, test requirement is an entity you have to test at least once. Okay. So edge pair coverage, for this coverage criteria, the test requirement. Okay. So basically, each reachable path of length up to 2, including 2, has to be tested at least once. So not only individual edge, as you can see, is a generalization of the edge coverage. Okay, and we're going to say a specific example to show what this means. Okay, so this is a very simple control flow graph. Again, in the class, we're going to use this kind of abstract representation. But in your mind, you should know that this represents a program that basically has 2 if statements, right? You have 1 if statement represented by n sub 0. After that, you have 2 branches. After that if statement, you have a second if statement. You have 2 branches and then finish. Okay. So each control flow graph is a representation of a program that you could write. Okay. If you want to achieve edge coverage, okay, what test path you have to execute? If we want to achieve edge coverage, I want to cover at least each edge at least one. Can you select test path? Remember, each test path, like a path from an initial node to a final node, that corresponds to a test execution, right? So can you select in the graph, select test path that achieve edge coverage? Each edge has to be tested at least once, has to be executed at least once. You can say A, C, E, G. This would be one test path, right? That covers 4 edges in the graph. I can select the second test path. On the right-hand side would be B, D, F, H. Okay. If I execute 2 test cases such that these 2 test paths are executed, then I achieve edge coverage, right? Because every edge I have in the graph is executed at least once. Okay. So remember, like when you again, when you generate the test cases, you cannot only generate one test case typically, right? Typically, you generate multiple test cases, and each test case represents the corresponds to one test path. When we talk about how we can generate actual test cases for a given test path later, okay? But for now, each test path corresponds to one test case. Okay, so we ask you to select test path to achieve a certain coverage, like on the homework problems, on exam. Typically, you would have to generate multiple ones. Sometimes you could generate one test path, okay? But in more cases, you are going to have to generate multiple test paths. Just remember that when you try to test the program, you have multiple test cases, and not only have one test case. Okay, so keep that in mind. So now the question is that, so this is a test set which has two test paths, and each corresponds to one test case. That's a relationship. Okay? So the question is that, would this test set satisfy edge pair coverage? Every path of length up to 2, would that achieve edge pair coverage? Why not? Can you?
So I think it doesn't cover the path like A, C, F, and H.
Right. So you basically see every reachable path of length up to 2, right? If you look at the test requirements, okay, this would be like CF would be a test requirement you have to execute at least once. And this CF, if you look at here, this edge pair is not executed in any test path that you have selected. Okay, so it does not achieve edge pair coverage. Similarly, DE, so the cross pair, the two cross pairs are not executed. So this two test path achieve edge coverage but not edge pair coverage. You see the difference, right? Which one is better? Is like edge pair coverage better than edge coverage or vice versa? Edge pair? Any other opinion? So you need to be careful about these kind of questions, right? Especially in the context of software testing. Typically, as I mentioned, we're going to give you a hierarchy, okay, of different coverage criteria. There's no one coverage criteria which is definitely better, okay? In both cases, okay, it depends. Edge pair coverage, as you can see, if you execute the cross pairs, you're going to be more comprehensive, right? You could detect more bugs, but to achieve that, you have to have more test cases. You have to spend more resources, okay? So when you do testing, as I mentioned before, from a certain perspective, it's a trade-off, it's a balance, okay? You have to look at your project. You have to look at how much resources you have. You have to look at what happens if I have a bug. Can you afford the consequences of having like some bugs in it, right? We need to make a trade-off, make a balance. And that is why we, as you will see, like typically we give you multiple coverage criteria so that in practice you could make a choice. So we cannot say one is definitely better than the other. And again, I want you to have this mindset when you test. We're not trying to detect every possible bug. in your program. We're not trying to prove correctness. What we're trying to do is to maximize the confidence with the resources that we have. Okay? So if you look at the edge coverage, you could say, well, some bugs may only be detected if you execute this kind of cross space, right? That's possible. So when you do edge coverage, you're not going to detect that. But that is okay, okay? Because sometimes that's the only resources that you have, okay? You're not going to detect all the bugs in your program. So from another perspective, to evaluate the goodness of a coverage criterion is not like whether it detects all possible bugs in your program, okay? It's just trying to maximize the confidence with limited resources. And this is, because you can imagine this coverage is at the top, right? So basically, we're going to test every possible path in the graph. That would be very comprehensive, right? Just like when we talk about the combinatorial testing, you have the whole combinations. So, would this work, right? When we actually do this in practice. So if you look at this graph, as you can imagine, it's like a loop structure. Right? You have a loop that could be executed for I don't know how many times. So again, we look at the graph. I guess you can, in your mind, you can map this to a program that has a very simple loop structure. How many paths we have in this graph? How many? Two? Okay. Tell me which two.
N1, N1, N2.
Okay, so one is N0, N1, N2. That's one path. And then the other one is N0, N1, N3, N4, N2, right? Okay. Okay, let me ask you this. N0, N1, N3, N4, N1, N3, N4, N2 is this a path? Look at the definition of a path. If you have the slides, what is the definition of a path in a program, in a graph? That's test path. Yeah. Well, you can say test path as well, but what is the would this be a path or test path? If you check the definition. Yeah.
But apparently not helpful in testing.
Not helpful in testing. Why not?
Because we are going anyway from N4 to N1 to N2.
Have you ever had the situation that like the bug can only be detected if you execute the loop for more than once?
With the same numbers, with the same values.
The same, not necessarily what you mean by the same values, during the inputs. Well, definitely you're going to have different inputs, right? If you want to say, if you want to execute the loop once or twice, you're going to have different. You have to have different test inputs so that the program is going to behave differently. Right? Because how many times, like if you have a loop statement in your program, it could be executed once, twice, I don't know, more than, it could be executed for 1,000, 1 million, let's say in some programs, 1 million times, okay? Can you guarantee that if you do not have a bug, when you execute the program, the loop once, then you're not going to have a bug when you execute the program, let's say for 1 million times? You cannot guarantee, right? What does that say? It says the number of iterations you execute is important, right? Some bugs may require you to execute the loop multiple times.
Have some count on that.
Yeah, you have some count, you could make a decision based on like, if you want to be extreme in your, for example, in your loop, the body, you could have an if statement. If you are executing the loop for 100 times, then I'm going to make a wrong decision, right? Yeah, that's possible, right? But the point is that the number of iterations you execute, okay, matters. You cannot simply say it does not matter. Okay? But coming back to my original question, would this be a path? If you look at the definition of a path, the path is just only requires like two consecutive nodes. They have to be connected. That's the definition of a path. Yeah.
N4 is it connected to N2?
Okay, very good. Okay, so I think I got a typo here. Yeah. Would that make it a path? Can I do another one? See, N1, N1, N3, N4, N1, N3, N4, N1, N3, N4, N1, N2. Would this be a path? This is also a path. Can I do another one? So how many paths we have? You have infinite number of paths. So if you want to complete path coverage, you cannot do it, right? Because you have the infinite. Remember, each path represents the loop is being executed for one more time, right? That's possible again, okay? Again, like if you really think about the program, the number of times the loop executes, okay? Sometimes if you have infinite loop, right, you have a bug in your program, right? That's possible, right? And even it's not part, like if you have a correct loop statement, in many cases you only have a finite number of iterations, you cannot execute the loop infinitely. But remember, I want to emphasize, we are talking about what I mentioned as syntactic retrieval. We only look at the graph structure. We do not go inside the code to do semantic analysis. Again, the reason why we do not do that is because that is undecided. I don't know if you have studied the halting problem. It means you cannot determine how many times the loop is going to execute statically, okay, without executing it. So we are only, I guess the point I'm trying to make is that we are only going to do like path selection, like we are only look at the graph. Okay, we cannot consider the semantics of the code that is represented by the graph. So how we're going to address this problem? Okay. So what we're going to do? Okay, I just gave you a general direction. We're going to discuss the details next. But the general direction is that we need to make a good trade-off. We're going to generate a finite number of test requirements. Okay, and we're going to preserve the fault detection of, okay, to some to a significant extent. Okay, so that's the basic idea, and we're going to discuss the details. We have two important concepts. One is called a simple path. So you can look at the definition of a simple path. Okay. So one way to understand this concept is that the single path cannot have internal loops. So inside the path, you cannot have an internal loop. Itself could be a loop. Okay? But you cannot have internal loop. a loop that is completely contained inside the path. But the formal definition is this: no node can appear more than once in the path except the first and the last node. In that case, the itself is a loop. Okay. If it's not, we use this as an example, right? So if you look at this one, okay, I guess this should be N1, right? This N1 over here. So I'm going to use this as because this example is synchronous so that you can get a better understanding. So this node this node appears twice in the path, right? And if you visualize, so this is basically a loop, right? When the same node appears, then you have a loop in the path. So this one, because this one is not the first node, this one is not the last node. Yeah. So this is the internal loop. It means outside the loop you have some other node. Okay. Itself could be a loop. That is allowed, okay, by the definition. So I guess the way I would, because the definition is kind of long, I guess what you can remember is that a simple path is a path that does not have internal loop. Okay, itself could be a loop. Then, yeah.
So does that mean a simple path has only one path? Or it can have many, like, I mean, suppose we have like a path going from N0 to N1, and then from N1 to N2, and we have the other path from N0 to N2 here. Like this way, you know, like from N0 to N2, and we have like one from N0 to N2. So is that a simple path?
Whether it is a simple path, okay, you just check the definition. Let me try to get a better understanding about what you are trying to ask. Okay. But the fundamental principle is that just check the against the definition. Okay. So what you are saying is that you have N0 go to N2, and you have another N1 and go to N. Is this what you have in your mind? So first of all, what is the path you are talking about? Whether the path you want to check, if it is a simple path, what path you are talking about? Can you give me the path? Yeah.
So in this case, like N0 is like we have like two times, right? Like from N0 to N2 directly, and then from like N0 is repeated again, right?
Well, give me a sequence. The path is a sequence. Give me a sequence of nodes. If you want to, because we are trying to check if the path is a simple path or not, right? Give me that path that you want to check.
N0 to
Okay, this is the N1, sorry, this is N2. Okay. N1, N2. Is this the path you want to check?
with the other one, I want to check. Like I want to compare between that two different paths.
Okay, so this is one path you want to check. You have another path, then 0, then 2. So first of all, these are two paths. This is not one path, okay? So if you want to check if this is a simple path, you just check the definition. Can you check the definition? Would this a simple path or not? So basically, the definition is very simple, right? No node appears more than once. Do you have any node appears more than once? That is a simple path. Okay? You can do that for the second one. You can check the definition. Is that a simple path or not? Okay. So I guess probably why you are asking this question, because you are thinking about this structure instead of you were asking like whether this structure is a simple path or not. But this is not a path. Okay, this is a graph structure. Okay, remember the path has to be a sequence. Okay. And that's what I suggest you guys to do. Like sometimes you are not sure like whether something is a given concept. Just go back to the definition and check whether it satisfies the definition. Any other questions? Yeah.
For the previous graph, we had only the first one, N0 and 1, and 2 is the sample
Yeah, among the paths that we look at here, only the first one is a simple path. Because all the other paths you have a loop, internal loop inside it. Yeah, that's right. Because for all the other paths, the one is going to appear for more than once. So the second concept called the prime path. One way to understand that is the prime path is a maximum simple path. So that means no other simple path could properly contain this simple path. Okay. So two requirements. The prime path has to be a simple path. Okay. The second requirement has to be maximum. You cannot find another simple path that properly contains. When I say properly contains, it means it cannot be the same. Okay? It has to have one more node in the path. Okay? In the path that contains this path. Okay? Yeah. Another point I want to make is that when I say a maximum path is not a longest path. Okay? Does not have to be longest. It only says you have to go by the definition. It only says no other simple path could contain this one. We're going to see examples. Okay, we're going to see examples that are not the longest one, but they are maximum because no one else can properly contain this one. We're going to see a specific example. Is that the question you were trying to ask? Or how? Yeah, the longest. Yeah. So remember, maximum does not mean longest. Okay, we're going to see example. Remind me when we look at the example. Then we have the new coverage right here. Prime path coverage. We are going to try to cover every prime path instead of every possible path. Why would we do that? Can anyone guess? Yeah, with loops. See, now it does not allow, at a very high level, does not allow internal loops. That will make the number of prime path finite. Okay. If you allow internal loops, you are going to have like an infinite